So this is the part 2 of the June 2015 Regents, and what we're going to do is review the entire part 2, like I've done with the multiple choice, but I want us, as we go through this, realize that this part 2, which some students feel like is very intimidating, is much like the multiple choice. It's the same concepts. So as I go through this, think about the concept behind this. And if you take enough of these practice tests, you'll find that this part 2, essentially, these questions could be in the multiple choice section. So if you're a big fan of the multiple choice but hate the part 2, think about the concepts. So let's be crazy and start in order. Let's go with 51. In number 51, what we have here is a part B2. And in this question, we don't really have any background information, so it's a straight question. It says determine the volume of a 2.0 molar HCl. And this should scream to us acid. And the reason why it screams to us acid, because this H in front, and hydrochloric acid is something you probably should have been talking about in your test and your course this year. Required to completely neutralize, a very important word. Okay, neutralize 20 milliliters of NaOH, and this is a base, something you should be able to recognize. And how do I know? Well, when I see a metal like sodium with a hydroxide, it's one of those strong bases. So what is neutralization? Well, if we take an acid, and if you think about the Arrhenius definition, the most simplest definition, you produce H pluses in solution. And this base is going to dissociate into hydroxides. And why is this neutralization? Well, acids which produce a high concentration of protons, or H3O+, we should be aware that this H3O+ and H+ are synonyms, are synonymous, water holding on to a proton or proton itself. These are highly reactive and can break bonds. Same thing with hydroxides. These are very dangerous as well. So high concentration, and you should recognize a molarity is a concentration. It tells you how much of that is in water. Look at that aqueous. That means mixed with water. So these are actually pretty high concentrations, and we should recognize the fact that whether it's a high concentration of protons from an acid or a high concentration of hydroxides from a base, individually these guys are dangerous. We call this very acidic. We'll call this caustic. We use liquid Drano, which is hydroxide ions, to break down all the different kind of components that are stuck in our drains. And of course, we know how powerful acids can be. So as dangerous as these can be at high concentrations, when you add them together, what you get is just water. So an acid and a base will neutralize themselves to become water, and we know how important water is to us, but also how harmless it is to us as well. So something as dangerous as an acid and a base becomes neutralized, okay, by becoming water. Now, I'm giving you this background because I want you to understand what they're after. So where do we have acids added to bases? Well, we have them in something called titrations. And a titration is normally a scenario where we have a known amount, let's say, of a base in a burette, okay? So we're going to add base. And that base we'll just say is NaOH. Now, it's not always set up this way, but this is the classic case. And we have some base in our burette. Then we have a beaker. Let's say that beaker has some amount of acid. Okay? And that acid, of course, has the H+. Now, of course, when we drop the base, there's hydroxide ions that we're dropping. And we're neutralizing. And we might add an indicator into this solution to recognize, hey, how much volume of this base do I need to exactly neutralize the acid? Well, if I know the acid is 2.0 molar, that's the concentration, and I know the base is 1.00 molar, which means the acid is twice as strong, and we have 20 milliliters, let's say, of the base being added. You could actually understand this. If I'm adding 20 milliliters, okay, how much acid what do I have? Well, if the acid is twice as concentrated, okay, then you can figure out clearly that you need half as much, and the answer would be 10. But you don't have to do these mental thought processes because we're doing a titration, we're adding an acid to a base. There's a formula we can use to clearly do this. So let's go to table T, where it gives us all of the formulas that we need mathematically to do these problems. So here we're at table T. Let's go down, and lo and behold, we have right in the middle there the titration formula, where we have the molarity of my acid times the volume of my acid equals the molarity of my base times the volume of my base. And there they go. So let's go use that and go back to the test. So here we go with my formula, my titration formula I got from table T. MV of the acid equals MV of the base. And here's what I have. I have a 2 molar HCl solution. Okay, so there's my 2 molar solution. They're trying to solve for the volume, so if you want to use X as your unknown, be my guest. Okay, and we have a 1 molar solution of my base, and we have 20 milliliters of it. Okay, so do your math. 1 times 20, put that in your calculator, I bet you get 20. And then we get 2 times X, 2X. Solve for X, which is really dividing by 2 in this case, and then we get X equals 10 milliliters. And certainly we did that in our mental math or a mental understanding of the problem, but this is a classic math question, not hard. The hardest part is identifying when I use this formula. So you're going to see this question definitely on your test. It's one of the most common math questions. So the answer is 10.0. So let's go to our answer booklet. And 51, very simply, is going to be 10.00. Now you say, Mr. Grodsky, what about all those sig figs that we learn about? Yeah, you learned it and it's great, but they didn't ask for it, so you didn't have to put 10.0 milliliters to get your 1 credit. Okay, so 10 would have worked just fine. All right, so any number of sig figs close to 10 would be accepted unless the question asked for it. So 51 is 10, so 52. Number 52. Determine the mass of potassium nitrate, KNO3, that dissolves in 100 grams of water at 40 to produce a saturated solution. Okay, another important identification type problem here. Now, how do I know where to look, where to go? Well, my first key is they said saturated solution. And when I hear the word saturated solution, bells go off. And the bells that I'm thinking about is a certain graph that we've dealt with, a solubility curve. And in a solubility curve, you should have learned that when you're on the line, you have a saturated solution. This would mean the number of grams of, let's say, KNO3 at a certain temperature. See, when they give me information like saturated, unsaturated, supersaturated, I'm thinking about table G, one of my favorite tables. Now, if they're giving me a temperature and they're giving me the grams of the substance, which they really are by saying saturated on the line, and of course they're telling me in how much water, okay, they're giving me a lot of information. How much water is this in? What temperature am I making the saturated solution? And what kind of substance? When they're giving you those 3 or 4 different types of information, or those 3 out of 4 pieces of information, you know you have a table G problem. And again, you've done these. I know you've done these. It's just a matter of recognition. And another classic question that could come up, not as often as the one we've just done in 51, but something you need to be aware of. Like I said, this could be a multiple choice question, just like 51 could be. So sometimes they'll tell you table G, and sometimes they do not. So any case, we're going to have to go there. So knowing that we're at 40 degrees Celsius and 100 grams of water, they want to know what the mass is. They want to know what this gram is at that temperature. It's that simple. So that's why you have to practice. Let's go to table G. There's table G, and there's potassium nitrate, KNO3. So there's this curve here. And one thing I like to see with table G is right over the curve sometimes. No, you're dealing with this curve. Sometimes these curves can get really, really messy with all the other curves. But what they say, at 40 degrees Celsius, okay, it was saturated, so on the line. Super would be above, unsaturated below. In 100 grams of water, note this curve, this entire graph is based on 100 grams of water. I mention this because they could have said 50 grams of water. And if you remember, if you have half the amount of water, you're going to have half the amount of solubility. Solubility is the ability of the water, the solvent, to completely dissolve the solute particles and mix it into its watery solution to make that homogeneous mixture, that aqueous. So at 40 degrees Celsius, being saturated with potassium nitrate, okay, so I go to 40 and I go all the way up and I see there's my value, and all I'm going to do is go across and try to make a good guess here. Looks to me a little less than half, so maybe 64 grams is the amount of grams. Remember, these are the grams of the solute particles mixed in 100 grams of water at a particular temperature. That's what table G is about. All right, so it looks to me that at 40 degrees Celsius, okay, I'm dealing with a 64 grams of potassium nitrate. Okay? And if you don't quite see what I'm talking about, you're kind of basically taking a straight edge, although I'm not good at drawing straight edges, and we're going across like that. And we're a little less than halfway, so again, 64. All right. So I put my 64 grams. Now that was an estimate, and they do allow for a range, but I would definitely take the edge of my test booklet and try to find it, because they're only going to allow a small range, sometimes very small. In this case, they were allowing 62 to 66 were acceptable ranges for that question. Okay, didn't need the units. Okay, I know your teacher may have made you use the units, but interesting enough, they didn't ask for them. Okay, sometimes they do, but in any case, 52 is 64, 53. In number 53, state in terms of molecular polarity. Can't say this enough. They are screaming to you how to answer the question. So you must answer it in the way they want you to. They say state in terms of molecular polarity. So you're going to have to answer your question based on molecular polarity. Now, really quickly, what's molecular polarity? It's a molecule which is an exact shape, an exact number of atoms, kind of like water is a molecule. There's 3 atoms, it has a particular shape, and this is the particle. Okay, ionic compounds make crystals, which repeat over and over again. They're not molecules. But what's the polarity part? Well, the polarity part means that we're going to have a larger distribution of electrons on one side of the molecule than the other, and that side gets a negative sign. Okay, I'm not sure why I started that one. And the other side that has less electrons, because it doesn't have the same amount of negativity, we say it's actually positive. And if we have another molecule that we would draw that has less electrons on one side and more electrons on another, an unequal distribution, this negative will attract to this positive by something called intermolecular attractive forces, or IMFs, intermolecular forces. These are not bonds. Okay, so in terms of molecular polarity, you need to understand when things are soluble, it's because we're dealing with the similar solubilities. If this molecule has a positive and negative end, and by the way, so does water, which is their universal solvent, it's got a negative and positive end because of the what? Unequal distribution of electrons made by these polar bonds and asymmetrical shape. These guys will mix very well, because if water is polar, has a negative and positive end, and ethanol is polar, has a negative positive end, you can clearly understand that water is going to interact with these molecules and surround them and be able to dilute them equally throughout to make something called a solution, which we say aqueous. And one way to remember this is that what? State in terms of like dissolves like. So you could say in terms of molecular power, because what? Water is polar and ethanol is polar, they will both dissolve in each other. So what you write here is water and ethanol molecules are polar. You couldn't just say like dissolves like here. That wouldn't give the right answer because you're not speaking in terms of what? Molecules and polarity, molecular polarity. So all they wanted very simply is water and ethanol molecules are polar. They're both polar. And you understand the reason why that works is because the positive end of one would attract the negative end of the other. And of course, they would have interactions. Water and oil or fats and water don't mix because one has positive negative ends, the water, and fats don't. So that's all they want. There's an easy answer to every single part 2 question. I've never seen a part 2 question where you're like, wow, that was amazingly difficult. No, there's an easy answer. It's just a matter of decoding what they want. But listen to the instructions in terms of molecular polarity. Number 54. Number 54. So now we're getting into an area where we have a little blurb and some information. And a lot of students get intimidated by these areas. And again, don't be intimidated. There's always an easy answer for every one of these. You're just going to have to unravel the mystery, so to speak, or peel back the onion if you like that phrase. I don't. In any case, identify the physical property. So I like to kind of go right into the question. And if I don't know the question, I go back into the reading to see and not get myself all tangled up. There's always so many of these questions where they give you too much information. And sometimes it's information overload and you psych yourself out. So identify the physical property, and that's important. They want a physical property in the table that could be used to differentiate. Differentiate, a fancy word, is to see how one differs from another, the samples of the 3 elements from each other. So, okay. So what we have is we have phase, we have mass, we have density, and then we have their formula. Okay, now physical property has to do with a property when we test for it or look for it, we don't change the substance. A chemical property is one that deals with its chemical formula and how it changes. So this one right here, the oxide formula, the reason why D would make this formula with oxygen or E would make these formula with oxygen or Q is how they react chemically. So you need to understand that oxide formulas are chemical formulas, how they interact and how they form bonds and break bonds and make new bonds. That's what a chemical change is. A mass and density are classically physical properties. When we look at the mass of D or any element, we're not going to change it. It's a physical property. Notice the mass are similar here, so I can't put mass. Okay, that's called a physical extensive property based on the size of the sample. Now, here's the winner. The winner's density. We can see that the density is different for all 3. And when we look and test for the density of elements, we don't change them. We don't create bonds. We don't destroy bonds. We don't make a new substance. So therefore, density is your physical property that you can see is different from the all 3. We can use these densities to figure out who's D, E, and Q. Okay, so 54 is density. And there it is, number 54, right, density. Again, although mass is a physical property too, as volume is, color, and all different others, melting points, density is the best choice, was the only one there that was different. Okay, so number 54 is density. Number 55, identify the group. Now you should know that a group also is called a family, and they are a family because they're related to each other. And if they're related to each other, they're similar because they have the similar number of valence electrons. Okay, so they're going to be in the same column, okay, on the periodic table. Now, okay, Mr. Gratzky, I got all that, but how do I know which column they belong to? It's element D, E, and Q. They don't exist. I can't look for them. The key here is the oxide formulas. The formula that they make tells you the charge they like to become. So if I look at D, I see it likes to become D2O. Now if it's D2O, I'm going to find the oxidation state of D. So what's the oxidation of oxygen? Well, periodic table tells me. So as I go to my periodic table of elements, like the one you have for your test, you're going to see that the charge that oxygen likes to become is -2. So that's my starting point. So I put -2 here. Now, when I assign oxidation states, I use bottom numbers to get the overall. Now, D2O as written has no charge. It's not a polyatomic ion, so it has to equal 0. That's the key. Because each oxygen, when bonded, is -2, and there's only one of them, the bottom number, -2 overall, is -2. -2 plus what number is 0? +2, obviously. But because the D's, which are contributing to the positive, and there's 2 of them, well, if there's 2 of them making the overall +2, each D must be +1, and that's the key. Okay, so now I know, party people, okay, that this element likes to become +1. So all I got to do is find what what column, what family of elements like to become +1. And we see group 1, this family 1, also called the alkali metals. If you're going to be fancy and show off, you could say the alkali metals, or you could say group 1. You can clearly see all of these guys love to become +1. All right, so group 1 or the alkali metals. So group 1 or alkali metals, no big deal. We write that right in our booklet there, okay? Either one is fine, okay? Number 56. So in number 56, okay, determine the percent error between the student's experimental density and the accepted density of element Q. Well, since they're giving me a table of properties of 3 elements, element Q has an accepted density of 2. I'm going to have to go back into the reading to see what the experimental, and there it is. A student's experimental result indicates the density of element Q is 2.10. So there's my experimental, and there is my known. And there we go. So I'm going to write that down here. So the student's, okay, experimental is 2.10. So that was the only question that I really needed to go back into the reading to see. 54 and 55, I was good to go right from the question. That information would not have made any sense to me until I know when I need it. That's why I like to go to the questions first. Okay, so we're doing a percent error. Now, a percent error is another formula that you could given to you in table T. So another place to look if you forget, and not a very difficult math question. So let's go there. So percent error, there it is. The measured value, which is the student's, this is the student's value, okay, minus the accepted value, which we get from the tablature, okay, times 100. So armed with my table T formula, the measured value, the student, is 2.10 minus the accepted for Q is 2.0 divided by the accepted value, 2.0, times 100, and you put that in your calculator, okay, and what you're going to get is 5%. And that's the answer. So you can see that we did a what? We did a percent error question, okay? And so the first page, not as daunting as maybe you think it is, okay? Straightforward stuff here. You just have to be able to identify. The key is identify these questions. Number 57. So we've got a little blurb here. We've got some information. Again, I kind of like to go directly to the question. Again, many students get lost in the sauce here with all this extra information. Go to the question, see what they want first. If you think you need something, go back. Compare the rates of the forward and reverse reactions at equilibrium. Now, if you think you can look up here, you can see that the system this equilibrium system, you can see the double arrow, but my friends here, I'm telling you, you didn't need any of this to answer this. This could be a multiple choice question. If you've done enough tests, you've seen the question where you say, which of the following is true about equilibrium, or something along those regards, okay? So the rates of the forward, so we're going to answer in terms of the rates, compare the rates, answer in terms of how they want you. Well, what do we know about equilibrium? Equilibrium is the forward rate equals the reverse. There's nothing more to remember about that. The best thing I love to tell my students is think of a line of what? Two people with, I guess, big necks, and a line of, I don't know, three people with small necks. Okay, whatever, it doesn't matter. And it doesn't matter if they have necks or not. But the point is, if I'm at equilibrium and I ask one person to switch lines every minute, okay, every time I check, there's always going to be two people on this line, always going to be three people. The people will switch, okay, but the amounts of each will stay constant. So there's two things to remember at equilibrium. Number one, the reactants and products stay constant because the forward rate equals the reverse. There's nothing more to it, okay? And you know that to be true if I've got a bottle of water and it's capped. Okay, you know if I put my eyeball next to it, the line won't move. The amount of water is going to stay the same because the what? Rate of evaporation equals the rate of condensation. Okay, so it's important. So back to the book. So in 57, because they asked for in terms of the rate, I say the rate of the forward reaction and the reverse reaction are equal. Okay, saying constant isn't speaking to the rate as they asked you. I just mentioned it because it's another question that can come up. So 57, I've seen this in multiple choice. It's just now appearing in your part 2. It's the same material. Okay, number 58. 58, state how the equilibrium shifts. And once you hear this shift, that should scream to you in terms of identification. We're talking about Le Chatelier's principle, right? Le Chat's, okay, where we have shifting. That means that one of the rates is now going to be faster to regain its balance. So what I like to do with Le Chatelier's type of a problem with shifting is I love to work in terms of this chart. Okay, and I think of it this way. I think in terms of this, there's a stress, and that's what humans do, and there's a response, and the response is what the reaction does. Now, the reaction responds by shifting to regain balance. See, Le Chatelier's principle basically states that when we apply a stress to a reaction by taking out SO3 or increasing the heat or whatever, the reaction responds by shifting to regain equilibrium. So what's the stress? The stress is, okay, we removed SO3, so we've lowered SO3. What's the response going to be? Well, the response is always opposite. Why? Because it wants to regain its balance. If I push you directly on you, no matter which direction, you're going to push back. So if I push it on your front side, you're going to fall over unless you push back opposite with your legs to regain your balance. If you don't, you fall over. Well, the reaction doesn't want to fall over, so it does the opposite. So what shift would cause my SO3 to increase so the reaction can regain its balance? Well, if you think with me, I'm going to shift to make more SO3. So the reaction is going to shift to the right. SO2 gets used up. O2 gets used up, and we're going to build up SO3, and more energy is going to be released as well. So the reaction is going to shift to regain its balance by making SO3. So this arrows up and down is the result of the response. My initial stress is what caused the reaction to go out of equilibrium, and the response, the shifting, is what the reaction does to regain its balance. So it's going to shift to the right. So I said number 58 that it'll shift to the right, but you could say a whole host of other answers. The equilibrium will shift to make more SO3, which is just saying that with my little chart, okay, that you're going to increase SO3, okay? It will shift to favor the forward reaction. It will shift to the right, and the concentration of the reactants will decrease. The concentration of the products will increase. All those things represent a shift to the right because we're going to increase the products. Remember, one of your products was SO3. Therefore, your reactants, okay, are going to go down as you make more SO3 if there's a shift. So many ways to say that. But really, think about it. It'll shift to the right. It's all I'm looking for. All they're looking for. And that's the correct answer. Again, these part twos are much easier. There's always an easy answer to every question. Have to unravel. Number 59. Number 59. Woo. A potential energy diagram for the forward reaction is shown in your answer booklet. So we're going to have to go there. In this diagram, draw a dashed line to show how the potential energy changes when the reaction occurs by the catalyzed pathway. Okay, this is a loaded question because the potential energy changes from the reactants and products will never change with a catalyst. The catalyst, as you know, speeds up a reaction by making a new pathway, and it lowers the activation energy. So this is, again, this could be a multiple choice question as well. And they could say, what happens when you add a catalyst? You lower the activation energy. Except in this question, they want you to draw the lowered activation energy. So let's go there. Okay, so here's our potential energy curve. Notice we're starting here and we're going down. We're finishing. So these are the reactants. Here's are the products. And if you remember your reaction, the energy was on the product side because it was an exothermic reaction, which is important to recognize that this is going down. You started high and you're going low, so obviously energy had to be released. That's why it's exothermic, just something to review. But the question was about draw, okay, what's happening, okay, in terms of a catalyst. A catalyst will not change how much energy the reactants have or how much energy the products have. Now, of course, I should speak in terms of potential energy, the energy in the bonds. So how much bonds or how much energy is in the bonds in terms of the reactants and products do not change. All the what catalyst does is find a new pathway that lowers the hump. As I tell my students, it medicates the pimple. Okay, so this is the unmedicated, uncatalyzed, and you can see that the activation energy, which is normally from where you start to the top of the hill, is here. Now the new catalyzed activation energy is lower. Now, of course, in this question, all they wanted was for you to draw this dotted line, and that was it. It's important to note that we do not change where we start and where we finish, just this pathway by lowering activation energy. Number 60. Number 60. Explain in terms of bonding why compound A is saturated. Now, I mentioned saturated before, and you say, oh, Mr. Grodsky, that must be a table G question. Yes, that'd be true if I gave you a temperature, heard the word solubility, but another place we called saturated. Now, again, saturated in solubility means that the water's holding on to the max amount of solute particles. But there's another way we can use saturated, and that means that compounds, okay, that are holding on to the maximum number of H's, okay? So in terms of bonding, if you look at saturated hydrocarbons or saturated compounds, we can see that this compound here has a heck of a lot more H's, all right, than this compound because of the bonding with the oxygen here. So this carbon, okay, could have more H's it's bonded to, but because it's bonding with oxygen or double bonding with the O or something else, it has less H's. So in terms of bonding, we can explain compound A is saturated because it's holding on to the max amount of H's. Now, the best way probably to talk about that is say that the carbon has all single bonds. If carbon all has single bonds, then it can only have the maximum number of H's. So many ways to explain why A is saturated, and you can say that there's single bonds between the carbons, or there's a max amount of H's. Now we talk about saturated organic compounds, okay, and I say organic because it's carbon-based. Table Q comes to mind. And here we are with hydrocarbons especially, and table Q is something I like to use because even though they don't come out and say it, alkanes are saturated. Look at this two-carbon system here. We have an ethane, eth for two carbons, which we get from the table above. There's my eth, okay, for two carbons. And then we have single bonds between the carbons, as we can see here, right here. That's why it's ethane. And anything that ends in an ane or anything that's an alkane, okay, is saturated. This is saturated. This is important. You're going to see this on your test, even in a multiple choice question or in a part 2. And why is it saturated? It has the max number. Look at this. This is C what? 2H6. Now, if you've got double bonds or triple bonds, because carbon can only make 4 bonds because it has 4 valence electrons, if you're going to have multiple bonds between the carbons, then there's going to be less bonds for the H's. This is C2H4, and this is C2H2. Notice the number of H's that are in the carbon chain drop as we add more bonds. So these guys are unsaturated. So the best way to explain in terms why something is saturated in a hydrocarbon or organic chemistry, carbon-based, there's single bonds between the carbons. Everything else with multiple bonds is going to have less H's. So all carbon-to-carbon bonds are single bonds. Or you could say the maximum number of H atoms are bonded to the carbon atoms. No multiple bonds. Many ways to say that here, and that's why part 2 sometimes is nicer to answer. You can say it many ways as long as you get the concept right, but I can't say again how many multiple choice questions have asked to pick the saturated hydrocarbon or organic compound, and you're looking for carbon-to-carbon bonds with the greatest number of H's. Number 61. Number 61. Explain in terms of molecular structure. That, again, they're screaming to you, they want you to answer in terms of exactly this way. This is the way they want you to answer. So in terms of the structure of how these things are bonded in terms of its molecule, why the chemical properties of A are different from the chemical properties of B. Now, I always say to my students, structure is king. You change the structure, you change its chemical properties, especially in organic chemistry, where like enzymes and three-dimensional proteins who run these reactions in our bodies and living organisms are based upon form and function. So structure is king. So the bottom line is A has a different molecular structure than B, and that would suffice. That's it. Now you could say that a molecule of B has a functional group that you can see in table R as an acid, and compound A does not. Compound A is an alkane, compound B is an acid if you look up that functional group. Okay, there's many ways to say it, but you could say very simply that they have different structures. Okay, and you can explain the carbon double bond to the O and OH, and this doesn't have it, this one doesn't. But it's all about having a different structure will change its physical and chemical properties. So I say they both have different structures in their molecules. Again, you could say the molecule of compound B has an organic acid functional group, and a molecule of A has no functional group. A molecule A has only single bonds. Molecule B has one double bonded oxygen atom. There's so many different ways you can describe how the structures are different, but that's the bottom line. Structure is king. Number 62. Number 62, and here we go. We've got this blurb again of information, a lot of times more than you need. So I go right to the question. 62, identify the decay mode of K37. Okay, now decay mode tells how K37, which is an isotope, a particular isotope, a mass number with decay, how it likes to, what particle it likes to give off when it changes its unstable nucleus to something stable. Well, my friends, we have a reference table that tells us how certain isotopes, what particles they like to emit when they're radioactive. So let's go there. So table N is our friend here. This gives us selective radioactive isotopes, and it tells us the decay mode. So this question was basically a question of, do you recognize the fact that I'm giving you a question where all you have to do is know that table N gives me that information? It's a recognition type of question. So K37 right off the reference table is B+. Okay, so you could say B+. Now, again, if I would say, I would say call it a positron, and if you didn't know that, you'd go to table O, okay, and you see that B+ is a positron. Okay, So that's the decay mode. It gives off a B plus or a positron. So table N in concert with O can tell you what that particle is. So 62, right from the reference table. Didn't need that blurb at all. B plus, which is the same thing as a positron, or you could have written the particle that's given to you in table O. Okay, but I get this directly from table N. That's all that question was. Number 63. Again, I know I have a blurb of information that I may need some information for, but I'm going to read the question first and see if I have to go back. Complete the nuclear equation in your answer booklet for the decay of K40. All right. All right, so K40. And let's go to the answer booklet. So in 63, they're giving me almost a finished nuclear equation of K40. Notice K40 is the same thing as the K to the 40 up top. The 40 is the mass number. So I don't need any information. 62, I didn't need it. 63, I just have to know how to do this. And in a nuclear equation, all the numbers on the bottom on one side have to equal all the numbers on the bottom of the other. So 19 equals negative 1 plus what? 20. 20 plus negative 1 equals 19. What number plus 0 is 40? Put in your calculator, I think you're going to get 40. Okay, but if you leave it like this, you're not going to get it wrong. You have to identify the element. This is natural transmutation. This nucleus, which is unstable, that's why it's giving off what we call a beta particle, is going to get more stable or having more stable nucleus by changing itself. So this is no longer potassium. Potassium has atomic number 19. This is atomic number 20. Okay, so where do you look to know what that element is? Periodic table, let's go. So K becomes calcium, atomic number 20. It's calcium. So Ca goes here. So 40, calcium 20. That's what you need in that box there. Okay, very simple question. And another question that has nothing really to do with the blurb above. Number 64. Determine the fraction of the original sample of K42 that remains unchanged after 24.72 hours. All right, so this is a half-life question. All right, and what I like to do with half-life questions, I like charts. I really do. And I'm just going to get rid, let's do the chart down here. Now this is going to be my 0 line. Okay, this is 0 time, 0 half-lives, and half-lives are the amount of time it takes for half of the sample to decay into something else. In number 63, K40 became calcium. So the time it takes for half of the original sample to become calcium, if that's the case we're talking about. Now, this of course will be 100% of the sample. Sometimes they'll give you that in grams, but because they're doing fractions, it's 1 over 1. Okay, so the total time they're giving me right here, the total time is 24.72 hours. Okay, great. In order to know how many halvings have occurred, I'm going to need a half-life. So K42, and they give me no half-lives here in my blurb, so I'm going to have to go back to table N that not only gives us decay modes, but also gives us half-lives. But this time I'm looking for, that's what makes this a little tricky, K42, not K37 or K40. So we have to look up the isotope of potassium, mass of 42, and what is its half-life. So K42 has 12.36 hours is its half-life. Okay, half-life you can see in this column. So 12.36. So if my half-life is equal to 12.36, that's the amount of time for each halving, and the total time is 24.372, I'm going to divide by 12.36, and what I'm going to get here by dividing these two is the total time is 24.72 and each halving is 12.36. You can see that when I divide by that, I get 2 half-lives. 2 halvings have occurred. So the first halving, I take my 100% of my sample and I cut it in half, which is 50% or 1 over 2. In the second halving, and I know that I have 2 because the total time is 24.72 and each halving is 12.36, the next halving I take half of a half, which is 1/4. And that's my answer. So 64 is 1/4, 25%, 0.25, all mean the same thing. Number 65. Number 65, show a numerical setup for calculating the atomic mass of potassium. Atomic mass of potassium. Atomic mass of potassium. All right, well, if I'm going to find atomic mass of potassium, what I'm going to have to do is something called a weighted mass problem. We know that there are, let's pretend that there's only, well, let's see here. Let's get the blurb. Maybe the blurb tells us. Okay, there are these many amounts of isotopes, okay, of potassium. So of these 5 different isotopes, potassium, 19 protons, but different number of neutrons, therefore different mass numbers, these are isotopes. But what they say in the blurb, of these 5, there's only 3 naturally occurring isotopes. These are the naturally occurring isotopes, okay, right here. And when we do a weighted mass problem, we take the naturally occurring isotopes, we use their relative abundances in nature to figure out the atomic mass of potassium. So to do this, very simply, and let's get rid of some things, what we're going to do is we're going to basically take 93.26% of 39 and add it to these percentages. So here's what it looks like, okay? So let's make some room for us, and I'm going to just get rid of the this half-life graph or chart that I had, not much of a graph, and let's do this. So very simply, we're doing a weighted mass problem. This is another classic math question that pops up very often and sometimes in multiple choice as well. So very important one to make sure that you know how to do. So we take 39, and I'm going to find 93% of that, so I move the decimal place 2 places, so 0.9326. Then I'm going to add that, it's another way of doing an average, to 40, that's the mass of this naturally occurring isotope, and I'm going to times it by that percentage. Remember, I'm moving the decimal place 2 places to the left, okay? So that'll be 0.0001, okay? And I'm going to add that to the next or third final isotope, which is 41, okay, times, again, 2 places, 0.06. And that's my setup. They didn't ask for the answer, just the setup, okay? So if you're going to do it the way that I did, you just have to make sure that you got your percentages correct, okay, or at least convert your percentages into a number to multiply by them. Now, some people would take these numbers and divide by the 100. You could have done real quickly 39 times 93.26, okay, and you could multiply these guys together and do the same thing. 40 times 0.01 plus 41 times 6.73, but because I didn't move the decimal place, I'd have to divide all of these by 100, okay, and that would give me the same answer. So again, understanding that this is a weighted mass problem, that's how you do this. You've seen this before. It's one that's in multiple choice a lot. Classic math question that pops up. I have a video that goes over the classic math questions, and this is certainly one of them. So you check that out if you want. But, okay, you should know the reason why potassium, okay, has atomic masses, or every element has atomic masses that have decimal points, is because of the weighted average. So when you go to reference table and you look up carbon 12.001 or whatever it might be, 1, 2, and I'm just guessing these numbers, the reason why you see a decimal place is because the atomic mass that we're rounding off is actually a weighted average of all the natural occurring isotopes using their relative abundances in nature. So what I should have put here as I got ahead of myself is use the actual atomic mass that they get for each of these. So in truth, I should change my 39 to 38.96. This should be 39.96 times this, and this should be 40.96 times here. And same thing with these values as well. So I don't know how they would take that. I'm sure these are the numbers I have to use here. And normally, if you don't have these numbers, you would take these masses and times it. So my mistake a little bit here, you just need to actually use the actual values of the masses here, okay? And I'll write that again in your test booklet. So again, using the actual atomic masses given, and then using the relative abundances in nature, okay? I didn't move the decimal place here because I was dividing by 100. We spoke of that. This is one setup that would get you the right answer. Number 66. All right, number 66, I've got myself another blurb of information. It's the very famous Bohr model, but again, I'm not going to go back into it until I see that I need to do that. State the atomic number and the mass number of this element. State the atomic number and mass number of this element. Well, we have to go back now. The nucleus of this atom contains 4 protons and 5 neutrons. So the atomic number is the proton number because all atoms are basically dependent upon what their number of protons are. For instance, to be carbon, you can only have 6 protons. In this case, we have 4 protons. So the atomic number is a 4, okay? And the mass number, okay, would actually have to be 9. Why? Because protons and neutrons have the same mass, so it'd be 5 plus 4 is 9, all right? And if we were go to table O, we can remind ourselves that neutrons and protons have the same mass. So in table O, okay, we have the protons, which have a mass of 1, and we have a neutron, a mass of 1. So they have the same mass number. So the entire mass of an element is due to the protons and neutrons, which again is really another example of a multiple choice question becoming a part 2 question. I've seen so many multiple choice questions where they want you to know that the neutron and proton have the same mass. Okay, now interesting enough, a beta particle is a fancy word for an electron. And there's the E. And we put a 0 here because compared to a proton or a neutron, their mass is insignificant. In truth, an electron is about 2,000 times lighter than these two. Okay, so there's number 66, and I can't say enough. I always like to say to myself, really? Really? And you're scared of part 2? Atomic number is the proton numbers. Yes, you had to know that. Yes, you should know the mass number is protons and neutrons. Table O can help you remember that, but really, number 67. Okay, number 67, state the number of electrons in each shell of this atom. So we've got 2 shells here. Let's go find this atom. Atomic number 4 is easy to find. 4 protons. Let's go find this element on the periodic table. So when I go find the element, I always look for the atomic number 4 because that's what identifies the element. Notice every element has their own unique atomic number, which is the proton number. Now, so it's beryllium. But more important, I notice the configuration is 2-2. What does that mean? There's 2 electrons in the first shell, and there's 2 electrons in the second, which kind of makes sense because if there's 4 protons, I always say, you say atom, I say neutral. Neutral, you say atom, neutral. Atom and neutral are always together. So 4 protons means you have a plus 4 in the nucleus. You need a negative 4 outside the nucleus, which is due to 4 electrons. So you've got 4 electrons that equal to 4 protons, and we know that 2 electrons fill the first. The configuration tells you that, party people. 2 in the first, 2 in the second. Okay? Again, I can say, really? For that question too, and we're so scared of part two? I mean, I'm telling you, these questions could be multiple choice as well. They're really the same thing. Okay, number 68. Number 68, using the Bohr model, which is electrons going in circular orbits around the nucleus, describe the changes in electron energy and electron location when the atom changes from the ground state to the excited state. Okay, I'll tell you, these kind of questions seem to be on every test. They need to, for you to understand how the electrons move, okay, and their transitions. So real quickly, we know that we have a positively charged nucleus due to all the protons. In fact, in this case, we have 4 protons, okay? And I know there's neutrons in there. For all intents and purposes, here's my nucleus. Then we have 2 shells. We've got the first shell that holds 2 and the second shell that holds 8. But what we do know is electrons, the first 2 exist here and the second 2 exist here. Now what you need to know is that electrons that are held closer to this positively charged nucleus feel that attraction to the nucleus more than those that are farther away. It makes sense. The closer these negatives are to this protons, the more that they're attracted to them, kind of like held firmly in place. They're being controlled by these positives more. That means these electrons have low energy. And if you have low energy, you're stable. You're not going to change your position because of your lack of energy due to the protons pulling. These guys who are farther away feel the tug on them less, so they have more freedom and more energy, and they tend to be unstable because they have more energy to do things. But back to the question, describe the change in electron energy and electron location. They are screaming at you on how they want you to answer the question. When we go from the ground state to the excited state, well, which side is the ground state? The ground state is the stable state. You're grounded. You have low energy. The bird isn't flying, okay? So this is the ground state. It's another word for the most stable state. And we would say this is the excited state. Excited means you have the most energy. So they want to know, describe, remember, you've got to answer according to what they want in terms of changes in electron energy and electron location. So when this electron jumps from a ground state to an excited state, which means what? It must go from a lower energy state to farther away to a higher energy state. In order to go from low energy to high energy, my friends in chemistry, you need energy. So energy is being absorbed here. So the changes in electron energy, the electron energy is going up because we're absorbing energy and we're going farther away. So they're not talking about whether we're absorbing or releasing energy, but they're talking about the changes in electron energy. So electron energy is going to go up and its location is going to be farther away. So in number 68, electron energy increases, change in electron energy. It increases because it's going farther away. Change electron location, electron moves farther away. In order for this to happen, they have to absorb energy. Okay, so again, you could say this many ways. Electron absorbs energy. You could say that. Electron absorbs energy. Okay. And in here, you could say electron moves to the higher energy shell, moves from the first to the second, second to the higher energy, farther away from the nucleus. Many ways to do this here. Okay. But I will say that this is a very important concept that I do see in multiple choice. They often talk to you about when an electron moves farther away back toward the positive nucleus, when it jumps from the excited back to the nucleus, that's an important piece because that's where energy has to be given off when you go from high energy position, this excited state, back to the lower energy position, the ground state. And that energy given off when you go in the reverse is that light energy or spectra that we can observe and use to identify elements based on the type of light given off. So that's something you see a lot. So this question was looking at the reverse when electrons jump away. Number 69. Okay, here's a blurb of information. Don't care. I'm going to go right to the question. Number 69, identify the element in urea. Oh, there's urea that makes an organic compound. Well, what makes organic compound is carbon-based atoms. So this had nothing to do with the question. You need to know what makes an organic compound is the carbon chain. That's why table P labels elements names based on the carbon chain. So 69, carbon, write it out, or the element symbol works for me. Number 70. Number 7, I know there's a blurb here, but the question says determine the gram formula mass of the product. Urea, there's the formula, the molecular formula, but they want the gram formula mass. They want the mass of the formula. What they're really asking for is how many grams per mole. So they want you to calculate the grams per mole here. Very simple. And again, you didn't need this blurb other than the formula to answer this. No reason to get what? Intimidated by these questions. So when you do a gram formula mass, which has a couple of synonyms, molecular mass, okay, atomic mass, which is elements, I add up all the individual atoms. So what I have here is I have a carbon. I have one carbon. And I'm going to 1 times its atomic mass. So we go to the reference table. And carbon has an atomic mass of 12.011. We're going to round that to 12. Nitrogen has an atomic mass of 14.067. We're going to round that to 14. And oxygen, we're going to round it to 16. So we're going to use the atomic masses. Yes, there are these, as we talked about it, these decimal places are because of the weighted average of the relative existing isotopes. But these numbers also tell me the mass per 1 mole of this element. Yes, so a mole of carbon is 12, a mole of nitrogen 14, and oxygen is 16. And that's what we're going to use to do the mass per molecule of 1 mole of it. That's what a gram formula mass is. So I have 1 carbon, so 1 times 12. You can check this out, is 12. Then I'm going to have 2 N's, 2 nitrogens. So 2 times that rounded number of 14, and that's 28. I have 1 O, and 1 times the atomic mass of oxygen is 16. I think that if I know my 1 times tables correctly, that's 16. And then if I have 4 H's, 4 times, now I know we didn't look at hydrogen, but hydrogen, if you look at the atomic mass in the reference table, periodic table in particular, you'll see it rounds off to 1. So 4 times 1 is 4. And then when you add these together, okay, you'd get a number 60. And it's 60 grams per mole is the unit, okay? And that's where we get this from. So that's the gram formula mass. Very simple math question, a very typical one. If you go through the video that I have posted in my channel that goes over the most classic math questions, this test is really following suit to that. So I'm just adding up all the atoms using their atomic masses to come up with this. Very simple, okay? And of course the answer is 60 grams per mole. Notice you didn't have to have that unit there. Don't let that fool you. Most of the time it's just a number. They're giving you the units. How nice. Nothing to be afraid of in the part 2, but you have to go over your classic math questions. Number 71. Number 71, write an empirical formula of this product. Well, the actual formula, if we're going to write this, let's go C, and there's only one of them, N2, there's H4, and then there's an O. Now that's the molecular formula. That's how it exists as its bonds, as its shape. The empirical you should recognize as the lowest ratio. Well, we can't reduce C1 into anything lower than a whole number ratio because it's one atom. So this actually is its molecular formula, how it exists in nature, and it's also its empirical formula. So it's kind of a trick question people got messed up on, but this is already its lowest ratio. Now, as a review, if I had hydrogen peroxide, okay, H2O2, that's how it exists in nature. Of course, its empirical formula, lowest ratio, would be a what? HO, okay? But water, H2O, exists this way, as we know from its bonding, that bent shape, that polar molecule. Its it exists this way, so that's its molecular formula, but it's also it's empirical because it just so happens to be the lowest ratio already. And that's what happened here. This was already its lowest ratio. I can't get anything simpler than 1, so it has to be CN2H4O. So 1C, 4 H's, 2 N's, and 1 O. And notice this, my ratio is different than the way I was counting up there. It doesn't matter what order you put them in, as long as they're the same exact ratio in the molecule, because again, I already had 1C to 1O. You couldn't reduce this to anything simpler. So this is the molecular and the empirical. 72. 72. Explain why this balanced reaction represents a conservation of atoms. So all chemical reactions have to have a conservation of atoms. And conservation of atoms means we don't destroy atoms. We do not make new ones. We just recycle ones from the one side to the other. We just kind of pull them apart and put them back together. So there's no creation of atoms, there's no destruction of atoms, and that's why we put coefficients to do that. So again, there's 4 questions here that really had nothing to do with the blurb other than using one of the formulas. But why a conservation of atoms? Very simple. The same number and same type of atoms are on both sides of the equation to show that there's been no destruction of atoms and no producing of atoms. We have the same atoms and same types on both sides. Number 72. Let's go to the answer booklet. And it's just as simple as this. No atoms are lost or gained. Again, you could say, if you want to be more wordy, there are the same number of atoms of each element on both sides of the equation. But again, no atoms are lost or gained. That's basically the conservation of mass. So there was 4 questions here that really were things you needed to know already, that the blurb really didn't give you much to give on it. So don't let the blurb of information get you down. Number 73. Number 73, I've got this blurb. I'm going to go directly to the question. State evidence that indicates the proportions of the components in rubbing alcohol can vary. Okay, well, this is something you could never know off the top of your head. We have to go back into the reading. Rubbing alcohol sold in stores. Here's the chemical formula. It's available in concentrations of 70% and 91% by volume. So different concentrations mean you have different amounts of rubbing alcohol mixed with the water. So state the evidence indicates the proportions of the components can vary. Well, they gave us 2 different concentrations. That means you have 2 different amounts of rubbing alcohol with water. Okay, it's just that simple. And they tell you to make 70%, you take 70 milliliters of 2-propanol with enough water to produce 100. Here you take what? 130 milliliter sample, a lot bigger amount of alcohol with the water. Okay, so clearly it's about those percentages. So 73 is a weird question. It's like it's a reading comp question. Nothing to do really with chemistry, but hey, we'll take it if you're going to give it to it. That is simple. So this had nothing to do with anything you've previously known, other than knowing that the different percentages are really the different concentrations. So that's basically it. There's nothing more to 73 than that reading comp type of question. 74. So 74, identify the property, okay? Again, they're telling you how they want you to answer of the components of the mixture. They're not really saying that, but it's a mixture of rubbing alcohol and water that makes it possible to use distillation to separate these 2 from each other, okay? Well, distillation is something you have to know. Distillation, and we did this in class, so we should have seen one. What we did in class, we took Coke, which is a mixture of sugar, water, a whole bunch of ingredients. We heated it on a hot plate, and this liquid, we were able to boil off the water from the solution. So the water boiled off first, and you should know that in a mixture, the components of the mixture retain their individual properties. So the water vaporizes, gets cooled, and becomes a liquid, and we were able to collect this water, okay, and boil off the water. Certainly you see this in how alcohol is distilled from the mash. If you watched all these crazy discovery programs where they're making moonshine in the woods, I guess illegally, but on TV, and somehow they don't get caught. It's kind of interesting. But the point is, you're seeing distillation working there. So why can water be able to escape while the other components of the liquid do not? Well, because they have different boiling points. Yeah, different boiling points. You're able to separate. Now, the best case or the classic case is that we get crude oil, okay, either from our own country or from other places. And crude oil is made of kerosene, lamp oil, diesel fuel for your home, gasolines. There's all different types of liquids that are in crude oil that we get from the ground. And what we do is we distill them, fractionally distill them, because they essentially, the liquids have different boiling points or different vapor pressures. So we're able to separate liquids because of their different boiling points, which is related to, of course, their different intermolecular forces of attraction. But it's about their boiling points, 74. So that's something you had to know, and nothing the reading could give you to do that, okay? So the boiling point is the property by which you could use distillation, because every liquid has its unique boiling point, and because you have a mixture, they retain their individual properties. 74. Number 75. So number 75, they want to say determine the maximum volume of 2-propanol in a 132 milliliter sample. Okay, the 132 milliliter sample of 91% aqueous 2-propanol. So that's how they made it. Okay, so what they're saying to you, if it's by volume, if you're saying it's 91% by volume of rubbing alcohol, then it's 91% of the 132 milliliter sample of the solution with water. So all they're asking you to do is to find 91% of 132. And when you do that, you're going to move your decimal place 2 places. We've talked about this in another problem. 91 times 132. Okay, and when you do that in your calculator, you get about 120.12. And we can round that to 3 numbers. They're not looking for sig figs, so they took any number around 120. So a lot of people, when they took this test, got this wrong. But remember what I keep saying, there's an easy answer for every question. What have I shown you so far? It's like, wow, that's crazy hard. This is easy. The hardest part, I agree, is identifying what you have to do, and that's why it takes practice to master this. 75, okay, is 120.12. And as you can see, it doesn't matter that it's 120 or 120.2. They didn't care about any significant figures. So number 76. Number 76, write a chemical formula for one compound formed by the combination of K plus ions with one of these ions as water completely evaporates in the seawater sample. So I'm going to have to go back into the blurb and see what's going on here. I have a sample of seawater is analyzed. The table below gives a concentration of some ions in the sample. So you got seawater. Now seawater is a mixture. You're going to have water and you're going to have these ions floating in this water, okay? And it's a homogeneous mixture, so the first drop is the same as the last. They're going to equally disperse throughout the water. Now what we're saying is, write a chemical formula of one compound formed when the water completely evaporates. So when we take out the water and water evaporates, these ions start getting closer and closer and closer to the point where you're going to see salt appearing at the bottom of a beaker if you're boiling them off, or a bottom of an evaporating dish. And you should know this. This is one thing you have to know. When you boil away the water, okay, you're going to leave behind the salt. One way to separate salts from water is to boil them off, okay? So what they're saying is, what will K plus bond with, okay, as I take the water out and these guys get closer and closer? Well, K plus is going to bond with things that are negative, because positives attract negatives. And if you notice, there's only what? 2 ions that are negative. So what would it make? Well, the K plus would hook up with, say, the chloride ion, and because K is +1 and chloride's -1, you'd make KCl. Or you'd have the SO4, notice it's a -2 ion, you would need 2 K pluses, and that would make potassium sulfate. And these are your 2 choices. They just wanted what? One compound. And how did they ask you to answer this? Write a chemical formula. So either one of these 2 would suffice. Number 77, determine the number of moles of SO4-2 ion in a 1400 liter sample of seawater. So look at the word. They give us moles and they give us volume. They give us moles and they give us volume. What? And they want to know what? Well, they want to determine the number of moles in a 14-liter sample of seawater. What I'm trying to get at here is that you've got moles involved, you got liters involved, and they're giving us concentration in big M. So what we're talking about here, party people, is we're talking about molarity and the formula of molarity. Since we're looking for the total moles, we're going to use the molarity formula. So the indicators for me, another, by the way, classic question in chemistry, where they want you to solve molarity or use the molarity formula. So my friends, in chemistry, molarity is equal to this big M concentrations, the moles of the solute, the substance being dissolved, over the liter of solution. And where am I getting that? So concentration right here, there's our formula. So in that problem, they want you to solve for the moles. You get the molarity from the chart, they gave you the liters. So in this question, SO4 negative, the molarity is 0.028. So 0.028 is my molarity, that's my M. The mole I'm solving for, that could be my X. And they have what? A 1400 liter solution. So it's a plug and chug, guys. I'm just putting the numbers in. So for the solve for X, I'm just algebraically timesing both sides by what? 1400 over 1. Or you're just multiplying by 1400 times 0.028. And when you do that, you get in your calculator 39. So you get 39, and we solve for the top variable here, moles. So moles equal 39. Okay? So another very typical math question, molarity, as we've seen others like percent, or we've seen the weighted mass problem, molarity, okay, conservation of mass, very typical math problems in this test. Number 78. Number 78, compare the radius of magnesium plus 2 ion with the radius of an atom. Well, what do we know? We know an atom of magnesium, electrons and the protons are equal. And then when it becomes what we call a cation or a positive ion, it lost 2 electrons. If you look at something called a half reaction, it lost 2 electrons. And if you have 2 less electrons, that means the remaining protons, which don't change because it's still magnesium, outnumber the electrons by 2, and they pull in the electrons. So you should know when you lose electrons, the radius gets smaller. Okay? The one way I help students remember this is when you lose weight or you lose electrons, you get smaller. So the magnesium atom becomes smaller when it's an ion because of the loss of 2 electrons. And I've seen this on so many tests where they even will ask you, why does the radius get smaller? Because you lose weight or you lose electrons. So and compare the radius. The radius is smaller. That's all there is. They're not asking you why. Okay? Because of the loss of electrons. Because by losing 2, like I said, the remaining protons who don't change, you're not gaining 2 protons. The remaining protons outnumber the electrons, and those electrons now can pull them in closer. The electrons feel the nucleus more. Okay? Any case. So again, the atom has a larger radius than the ion, positive ion. And you should know it's the opposite way. Okay, this is the atom, which is neutral, protons equal electrons. But if I have an atom that gains electrons, you should know an atom that gains electrons actually gets bigger, becomes a negative ion, because when you gain electrons, now the electrons outnumber the protons and pull away. Or when you gain weight, you get bigger, you gain electrons. Okay? Number 79. So using the key in your answer booklet, draw 2 water molecules. They're asking for 2. You've got to do what they say. Showing the correct orientation of each water molecule. That means both water molecules have to be correct toward the calcium ion. Okay? So you've got to answer based on what they ask. Draw 2 water molecules. So I'm going to draw the negative end of the water molecule, which is the oxygen end, the electron-rich end, because it's more electronegative and it pulls in the electrons closer. That negative end is attracted to the positive calcium ion, and these are called molecule ion attractions. Okay, if this was a chloride ion, a negative ion, you'd have the positive part of the water oriented toward that negative, if you see it that way. Remember, water is polar. It's got electron-rich area, that's negative, and electron-poor area, that positives. Okay, so that's what they were looking for there. All right, number 80. Boy, I've seen this question before. Explain in terms of ions why gaseous reactant, okay, the gaseous reactant, gas, reactants are on the left, okay, in a forward reaction, is classified as an Arrhenius acid, okay? Now, Arrhenius always drives people crazy. I forgot that person, I don't know him. Very simple. It's the simplistic definition of an acid, which means somehow HCl produces protons in solution. Somehow. They're not talking about donating or accepting. That's another definition. The simplest definition is acids, which, by the way, put an H in front to remind you, to scream to you, I give off H pluses. So the simplistic or simplest definition of an acid is that you produce H pluses in solution. That's the Arrhenius definition. Now, if you wanted the Arrhenius base definition, you'd produce hydroxide ions as the only thing negative in solution. But the acid definition, you're H pluses. So I've seen this in a multiple choice question millions of times. Now it's, again, part of part 2. So the most simplistic answer for Arrhenius is it produces H plus ions in water. Okay, so that's just it. Number 81. 81. What would be the color of bromocresol green? That's a acid-base chemical indicator found in table M. If it had been added to the water in the flask before any of the acid was bubbled through the water. So in the flask, before you add the acid, is just water. In water, pure water with nothing added, the pH is 7. Okay, so let's go to table M and see what the color of bromocresol green will be when the pH is 7. So bromocresol green, here we are, and when the pH is 7, that means it's 5.4 or higher, it's blue, right? Yellow to blue. So blue is 5.4 and higher, and 3.8 and lower would be the yellow. That's how you read that, right? So the first color is for this and lower. The second color is for this side and higher. So because it's above 5.4 pure water, it would be blue, okay? Yep, table M question right from the table, 81 blue. Number 82. 82. Compare the hydronium ion concentration of the solution that has a pH value of 3.0 to the hydronium ion concentration of that of water. So if you have a pH of 3.0, you're below 7, which you should know is acidic. And if it's acidic, there are more H pluses than there are hydroxides. So hydronium, okay, is not an H plus, but it's synonymous with that because water will hold on to an H plus if it's produced by the HCl and make something called H3O plus, which, by the way, is the hydronium ion. In table E, which is the table that lists polyatomic ions, hydronium is. So the hydronium ion is linked to an acid. So when you have an acidic solution, it is because you have a lot of these protons, which wind up being a lot of H3O pluses. So there's a lot more H3O plus in the solution than there is water. So the hydronium ion concentration is less in the water, or the hydronium ion concentration is higher in the solution than the water. Many ways to say this. You can also say that the acidic solution is 10 to the 4 times greater than that of the hydronium concentration in the water. Many ways to do this, but they just wanted to compare. The more acidic solution has more of them. That's pretty simple. Okay, number 8. Okay, not one of my favorite questions of all time, but we can handle it. State the direction of flow of electron flow. Well, this is a battery, only because I know that its energy is being used to make the clock work. It's a potato battery. Very cool, yes. But, okay, what do I know? I do know that zinc is a standalone metal. It's going from 0 to +2. And how does that happen? How does zinc 0 go to zinc +2? It must lose 2 electrons, right? Its charge is going up. Notice I put the 2 electrons on the half side of the reaction to show that both sides are 0. So this is losing electrons. You know, Leo the lion says grr, so this is getting oxidized. Electrons flow from the chemical species that releases electrons to the side that accepts them. And we have another mnemonic called anox red cat. So the zinc must be the anode. Anox, it's the place of oxidation. And electrons always flow from the anode to the copper, which must be the red cat, the cathode. So it must go from the zinc-coated nail, okay, to the copper rod. Okay, and of course it's happening 2 places here, but it doesn't matter. Electrons are flowing from the zinc to the copper rod, from the anode, the place that loses electron, to the cathode, red cat, to the place accepting them. Electrons always flow from the anode to the cathode. All right, so a lot of confusing stuff in here, but when you look at the reaction, it's clear that the zinc is oxidizing, H+2 is getting reduced, okay, and the zinc is the one that's the anode. Even though the copper is not part of the problem here, we know copper is the electrode where the reduction, red cat, takes place. Okay. So zinc to copper. Now, as I'm thinking about this question, you could have also looked at table J, which lists the activity of zinc and copper, and zinc is higher than copper, which means zinc is better at being an active metal. It's more active. And what do metals do? Metals lose electrons. They oxidize. So the higher you are on table J, the better off you're going to oxidize. That means anox, you're going to be the anode, if you look at it that way too. But they gave us the reaction. So zinc is more reactive than the copper based on table J as well. So it goes zinc to copper, another way to look at it. Okay, 84 is a classic half reaction. We had a nuclear equation, so we have zinc 0 on this side of the reaction becoming, on the other side of the arrow, zinc +2. Rebalancing the mass, 1 zinc, 1 zinc, we have to balance the charge. This side is +2, this side is 0. So I put in 2 electrons here because a -2 and a +2 gives me 0. This side is 0. So when I'm putting my electrons in, I put them in so that both sides of the half reaction have the same charge. So as I talked about before, zinc is losing electrons for its charge to go up. And this is the half reaction that occurs, okay, at the oxidation. And of course, we have identified that to be the anode, oxidation, anox. And there it is, pretty straightforward, 84. Number 80. So this stumped a lot of students. Why would the battery need phosphoric acid? Well, if you remember, all batteries require a salt bridge. And salt bridges allow what? Ions to flow. Oops. And the ions have to flow to keep both sides of the half cells from getting positive or negative. Remember, the reason for the ions to flow in a battery is to maintain electrical neutrality. We don't need one side of the potato to become positive or negative. That will stop everything. So in order for electrons to flow to this side of the battery, this battery cannot be negative. So we need positive ions to flow, okay, in order to neutralize any negatives that build up on this side. So the bottom line is the phosphoric acid is an electrolyte that allows the both sides of the half reactions to maintain an electrical neutrality. You can think of this in terms of just total salt bridge. It gives it the ions so they can flow. It acts as a salt bridge. All the above work, okay? So it allows and releases ions that are free to move to act as a salt bridge. So it's a tough little question because the setup is so weird, but what does a battery need? It needs a salt bridge. It needs ions to flow, and phosphoric acid, by the way, is an acid, and we've learned that acids, okay, are very strong electrolytes. This one's going to break apart into protons, and then H2PO4 negative -1. So you're going to make a lot of ions. Acids are very, very good electrolytes because they dissociate into ions, and electrolytes are things that conduct charge because of their free moving ions. So all the above things work here, although it seems very strange in the setup of the question. But they basically took almost anything that was connected to ions and ions flowing in salt bridge. So here it is, acts as a salt bridge. You could have said it's an electrolyte. It releases ions that are free to move. The H plus ions are reduced that come from the phosphoric acid. So even though it was a weird question, they accepted a wide range of results. Hope that helped, and I hope you looked at part 2 as nothing more than an extension of the multiple choice questions. Are there some weird questions that could pop up? Very far and few between. But even if they were, like you see here, they're accepting a wide range. This question's really about the salt bridge. All right, hope that helped. Good luck.